In the previous lecture, we introduced the central idea of quantum mechanics, and that is wave-particle duality. So, in this sense, we talk about what's called a quantum particle, which is the embodiment of the wave-particle duality. We want to use a wave to describe this particle. And we all know that the simplest of all waves is a simple harmonic wave, and I can write down a simple harmonic wave in this form, e to the I k1x, assuming that the wave vector of this wave is k1. You notice that I did not use sine or cosine, rather I used the exponential e to the I kx, introducing the complex variation. And that in fact is for convenience. You will see that the wave equation will be using complex wave functions. Okay, so here is a wave with a single value of k, or single value of the wavelengths. But in general, if a wave is not a simple harmonic wave, I can still write it down as a sum of simple harmonic waves in this format. You see here, this is an arbitrary wave, which doesn't have to be simple harmonic. I sum it up, or more precisely, I integrate over contributions from very small components. Each component has a vector, wave vector k, and its amplitude is psi tilde k, and I sum over. You know, this is the simple harmonic wave with a wave vector k, and here is how much it contributes, the amplitude. I sum it all up, then I get this wave. And this function, psi tilde, is often called the image function of psi, or we call it the Fourier spectrum of psi. Basically, what this function represents is what kind of contribution does a wave vector k, does a simple harmonic wave of wave vector k contribute to the original wave. So you see, I can go from psi to its image function and image function back to psi. This pair of equations is called Fourier transformation. This is well known long before the birth of quantum mechanics. This is a mathematical tool we use a lot in any wave analysis. And we're going to first do some mathematical review of the Fourier transformation, because it will be very useful in our understanding of the wave description of particles. The simplest wave, again, is a simple harmonic wave, and what I did here is I plotted the Fourier spectrum of this simple harmonic wave with a single wave vector k1. So in k space, the only component that survives is a component with a wave vector k1. So it shoots up to a very high value, but everywhere else the contribution is 0. So you get a wave that is exclusively made of this simple harmonic component whose wave vector is k1. And the wave itself is this, e to the I k1x. If I plot it, it looks like this. Okay, now what that means is that I can use a single component k1 to find a wave, to construct a wave which is infinitely long in x, in real space. So here is in k space, here is in real space, or the conventional space. And in this extreme example, you find that the wave is extremely localized or concentrated in k space, yet it is extremely delocalized because it goes to positive and negative infinity in real space. So you see the stark contrast between these two cases. So this is our first example, how we can construct a wave from a simple harmonic component using only, in this case, one simple harmonic component. Now you notice that I drew this particular Fourier spectrum for this simple harmonic wave. I drew a line which shoots to infinity, that's at least my intention is, at k1 and 0 everywhere else. So psi k should behave very strangely as something 0 and infinity and go back to 0. Even though this qualitatively makes sense, is it really true according to the Fourier transformation? Well, we can check that, can we not? We take this function, right, which is psi, right? We plug into the formula for its Fourier spectrum. So e to the I k1x, then times e to the power negative I kx, and integrating over dx, let's see what kind of Fourier spectrum I get for a simple harmonic wave. And I started out from here. It's a constant, whatever that is, square root 2 pi, whatever, I don't really care. E to the power I k1x, that's the wave function itself, times e to the negative I kx, and that integrate over dx from negative to positive infinity, and so that's what I get. Now, take a good look at this expression, e to the I, then k1 minus k, then integrating over dx. There is an x here. If k1 is not equal to k, then you can actually have an integration between negative and positive infinity. That's when x changes. And you can see here when x is very large, this function oscillates very, very rapidly, right? And the phase of this function is totally random. It can change very rapidly, and therefore when you try to add this function, what do you get? You get 0. When you integrate over this function, you get 0 because the rapid change, the randomness of the phase involved with this function. So it is actually 0 when you try to integrate, and that is when k1 is not equal to k. So let me write that down. It's 0 when k1 is not equal to k. But when k1 equals k, that's a different story, because when k1 equals k, there is nothing in the shoulder, on the shoulder of exponential is e to the power 0, and that just kills the randomness of the phase change, and therefore it's e to the power 0, which is 1. Integrating between positive to negative infinity, of course, you get infinity. And that happens only when k1 minus k equals 0 or k equals k1. So the Fourier spectrum indeed is 0 when k1 is not equal to, when k is not equal to k1, and infinity when k equals k1. So therefore, there is a single component in the Fourier spectrum, and that contributes, that shoots up to infinity, making up the only contribution to psi. So what you get is a simple harmonic wave with this particular wave vector k1. Now this function that I just got, in general has a name. We call it the Dirac delta function, or simply the delta function. The delta function behaves like this. It shoots to infinity at x equal to 0, and it's 0 anywhere else. Okay, it's 0 anywhere else. Delta x equals 0 when x is not 0, and it's infinity when x equals 0. And this is certainly true in our case. Before, we had delta of k minus k1, so when the argument of the delta function k minus k1 equals 0, which means k equals k1, you have infinity, otherwise you have 0. So that's a special case. That's an example of the Dirac delta function. The Dirac delta function is not a conventional mathematical function because it changes abruptly to infinity and changes back to 0. So mathematicians had a hard time accepting the Dirac delta function. You can well imagine this delta function was not actually introduced by a mathematician. It was actually first introduced by a physicist, Paul Maurice Dirac. So we call it the Dirac delta function. Dirac was one of the most brilliant physicists of the 20th century, and he was such an original person. He invented different mathematical symbols and mathematical expressions for quantum mechanics, among his many other contributions to quantum physics, which we'll see later. The Dirac delta function, again, was not well received in the mathematical community. The first mathematicians refused to accept this as a legitimate function. And later on, they realized, gee, this stuff is useful. They actually start to use it in solving differential equations and among other things. So eventually, they did accept this as not only a legitimate mathematical function, but something extremely useful. And we'll be using that throughout this course. The Dirac delta function, okay? This is, you see it for the first time here. Now, we saw this first example of an extremely localized wave function in the k space using a single k vector, no other k vector. And the result is an extremely delocalized wave function in x space. Going back to this plot again, extremely localized in k space and extremely delocalized in x space. So it extends to positive, between positive and negative infinity in the x direction. We can look at the other way around, another extreme case, and that is, what if I have a wave that is extremely localized in X space or in real space? How does it look like in the K space? So this wave, unlike a simple harmonic wave which extends between negative and positive infinity, it is at a single point. So it is a delta function in X space. Okay? If we use this wave to describe a particle, can you tell me what a particle is? Yeah, sure. The particle can be only found at location x1. It is not anywhere else. Okay, so it is extremely localized in X space. What is the corresponding spectrum, Fourier spectrum? So what kind of simple harmonic component should I use to describe this wave? Well, let's see here. I use a delta function, x minus x1, to describe the wave function in real space. So x can only be equal to x1, otherwise the wave function will go down to 0. This is the corresponding expression for psi k. In fact, it's also, there's a constant here because I did not use an equal sign. It's just a constant, which I don't really care that much. Psi x e to the ikx, and psi x is delta x minus x naught. So it's proportional to, okay, negative to positive infinity, delta x minus x1, e to the I, k, x, and then integrating over dx. So what is this equal to? Well, this entire integrand is actually mostly equal to 0 unless x equals x1, right? So you don't have to worry about what happens when x is not equal to x1. Just worry about when it is, because when x is not equal to x1, there is no contribution to the integral. When x equals x1, you can write this x as x1, of course, because x equals x1. And then that x1, of course, is a constant, so I take it out of the integral. And what do you have left? You have left with this delta function, delta of x minus x1 dx. So this basically is the area under this delta function. Okay, you're talking about the area integrated over this delta function, delta x. This is defined to be 1 for convenience. So this delta function is normalized because the total area under that curve is 0. You have an extremely narrow base, but extremely tall function. The area is basically something very small, something very large, and we give it a number 1 because that is for convenience. So you take that out, and you're left with e to the I k x1 only, right? And then what's left is the delta integral, which is 1. So I have an extremely localized wave function in X space. The particle is stuck here. What kind of simple harmonic wave should I use? Well, in the past, we looked at a single simple harmonic wave. It's a very pure harmonic wave. Now it's a different story because e to the I k x1. If you plot it in K space, it's going to look like this. Right? It's going to look like this. So whatever the value k, the absolute value is the same. You know what that means? It means the wave function describing this localized particle is not a single simple harmonic wave. Rather, it is made of equal contribution from all k values, this k from negative to positive infinity. You have to use an extremely delocalized spectrum in order to add together to construct a wave that is extremely localized in real space. So, looking back at these two extreme cases. Okay, let's look at them again. You can see, at least for these two extreme cases, you see a complementary situation here. A very concentrated wave in K space leads to a very delocalized wave in real space, and a very concentrated wave in real space, X space, leads to a very delocalized wave in K space. What about something in between? Neither of these two extreme cases. So the wave is not completely delocalized or completely localized in either the K space or the X space. Then what? Well, we have an example of such a case. So let's look at an intermediate case. Here we have a wave that behaves like this. Okay, it is 0 everywhere else, but except its it's a constant between whatever that constant value is between negative a over 2 and positive a over 2. In other words, if you use a wave like this to describe a particle, this particle can be found somewhere between negative a over 2 to positive a over 2 on the x-axis, but cannot be found anywhere else. Okay, so roughly speaking, the range where we can find the particle has the width about a. Now, what kind of Fourier spectrum does this guy correspond to? So we write down psi first. It's constant when x is absolute value is less than a over 2. 0 when absolute value of x is greater than a over 2. Using the formula for the Fourier transformation, I get a constant. These are not the same constant because there's a 2 pi or whatever. I don't really care. Negative to positive infinity, psi x e to the power negative I kx dx. I just have to plug that in. Okay, plug that in. Now when you plug that in, the range of integration shrinks. Instead of from negative to positive infinity, now I only need to consider the integral from negative a over 2 to positive a over 2. Do I make sense? Because outside this range, psi is 0, so I have to integrate. But within this range, psi is a constant, which I take out to combine with this. And then I'm just left with 1. Okay, e to the negative I kx dx. Now, that is not hard to do at all. You can integrate that, and here's what you get. This is the result of the integration after you integrate. Now, this e to the power I something minus e to the power negative I something divided by 2i. Some of you may recognize that. What that is just a sine function. Okay, using the Euler formula, e to the I theta minus e to the negative I theta over 2i equals sine theta. If you wonder where that comes from, all you have to do is express e to the I theta and e to the negative I theta in terms of infinite series. In fact, in terms of, not infinite series, just in terms of the Euler formula, e to the I theta equals cosine theta plus I sine theta, e to the negative I theta equals cosine theta minus I sine theta, and you will easily get that. So this whole thing is just sine of Ka over 2. Don't forget to divide by K, okay? And I can add A over 2 and put the rest of the constants over, so it's proportional to sine of Ka over 2 divided by Ka over 2. So you have a sine angle divided by the angle itself. This, as you know, is the sinc function. The sinc function of Ka over 2. So this is the Fourier spectrum for a wave like this. Okay, the sinc function, I have a plot here. The argument is k, and the sinc function itself is Ka over 2, so it looks like this. The sinc function has a peak in the middle, and then it gradually dies down. Now, this function does extend to infinity in theory, but the amplitude diminishes. So therefore, primarily speaking, the function is concentrated around here, around the first peak, right? And the first peak has an edge. This is the edge of the first peak, and this is where the argument of the sinc function goes to pi, so sine pi, that's the first 0 away from the center. And the argument of the sinc function is Ka over 2, so you let Ka over 2 to be equal to pi, therefore K equals 2 pi over A, as you can see here. And therefore, the width of this sinc function from here to there is roughly double that figure, and then we call that delta K. So delta K is roughly is 4 pi over A. Okay, so you see, I have a function whose range in the x direction in the real space is A, and I can use a bunch of simple harmonic waves to describe it, but the wave components, the k values of these simple harmonic components are roughly concentrated within a range of delta k. This is roughly delta k. And that delta k is about 4 pi over A. Now you notice that delta k is inversely proportional to A, and yet delta x is A itself, and therefore we say, in this case, delta x times delta k is roughly 4 pi over A multiplied by A. So it's about 4 pi. Okay? Don't take that 4 pi too seriously, because the range here, delta k, is not exactly between here and there. So this is just an approximation. But suffice to say that what we're getting here is a number which is not that far from 1. Okay, delta k times delta x is not that far from 1. Even though this is not quite the same as what we learned in the previous two extreme examples, we do learn one thing that is consistent, and that is, again, when a wave is highly concentrated in its real space, so A is very small, it will be more extended when you write down a Fourier spectrum or in K space. You see here, delta x goes like A, and delta k goes like 1 over A, right? So a more concentrated wave in X space leads to a more delocalized wave in K space, and vice versa. So this is why if you multiply delta k and delta x, you actually get a number that is not dependent on A itself. That is our first example of an intermediate case. So now let's take a look at another intermediate example. This, in fact, is physically more meaningful because we're looking at a wave function that doesn't really have any sharp edges. E to the power negative x over a squared. I ignored a constant in front of it, therefore I did not use an equal sign here. You can plot this wave function as a function of x. So it's really just a bell curve. It peaks in the middle and it goes down as you move away from the center, which is x equal to 0. And roughly speaking, the wave extends by about a on either side. When x equals a, the wave goes to e to the power negative 1, which is much smaller than 1. So we say, roughly speaking, the range of this wave in x space, or the whereabout this particle, can be found roughly in a range of about 2a from here to there. Okay, what is the corresponding Fourier spectrum of this wave function? Well, according to our formula, e to the negative x over a, that's the function itself, times e to the power negative I kx, then you dx integrating between positive and negative infinity. There is a little trick involved in solving this integral. You probably don't like this this I here, so let's try to work it out together. And it turns out you can change that to a cosine function, believe it or not. So here's what I'm going to do. I'm going to divide this integral into two sections, from negative to 0, and then from 0 to infinity, positive infinity, negative infinity to 0, e to the power x over a squared. Now, this is where x equals a negative value, right? Between here and there, it's negative value. So I'm going to write it down at minus I k absolute value of x dx. I put a negative sign in front of it just to guarantee that. Well, in fact, no, I should put a positive value here because x itself is negative, so overall I get a positive. And then you go from 0 to infinity, e to the negative x over a squared minus I k x. This x is also absolute value because it's positive anyway, dx. If you take a closer look at this integrand, e to the negative x over a squared plus e to the I k absolute value of x, this integrand certainly is an even function of x, right? When x changes to negative x, doesn't really matter. And therefore, I can change the range of this integral between negative infinity to 0 to between 0 and infinity, because this is an even function. So I'm just going to do that. So it's from 0 to infinity. It's just like that guy. It's also from 0 to infinity. So therefore, I have two integrals with the same range of integration from 0 to infinity. So I'm just going to add the two integrands up. E to the negative x over a squared. And then here is our first term, e to the I k absolute value of x. X is already positive. I don't need that absolute sign anymore. Plus e to the negative I kx. And then dx. Okay, so can you see the cosine coming in? Well, this thing itself, e to the I kx plus e to the I negative kx, in fact equals 2 cosine kx. Again, thanks to Euler's formula, e to the I theta equals to sine theta. Cosine theta plus I sine theta. So you divide this by 2, you get this cosine function multiplied by 2. So this in fact equals 2, 0 to infinity, e to the power negative x over a squared cosine kx. and then you integrate over x. Okay, this integral, I'm going to leave that as an exercise for you. It's not that hard to do. There's some constant in front of it, which I don't really care. What is important is the functional form itself, and it goes like the following. What you get turns out to be another exponential function, e to the negative power ka squared. Now remember, a has the unit of x, which is length, and k has a unit of 1 over length, so ka is a dimensionless number, which makes sense. So if you plot the functional form of the Fourier spectrum for this wave in k space, you're going to get something that looks like this. It's another bell curve in k space. Now, the range of this bell curve, roughly, that's when, just like here, I set x equals a when the whole thing becomes e to the negative 1. I can do the same thing here, e to the power negative 1. That's when k equals 1 over a, right? So it's 1 over a, roughly speaking. The range in k space, in other words, the kind of waves, the kind of wave vectors which I use to construct this wave has a range of roughly between here and there. There's a negative 1 over a to positive 1 over a. So it's roughly 2 over a. So let me write down the results. Delta x is about 2a, and delta k is about 2 over a. Don't worry too much about these 2's. These numbers change from example to example. So, but roughly speaking, delta x times delta k is about, actually in this case it's 4, but the order of magnitude is 1. Okay. So we see one more example where an extended distribution in real space leads to a concentrated distribution in the k space and vice versa. In fact, if I had a highly concentrated wave, which means a is very small in the x direction, in the x space, then I would have to draw something like this. Okay, that's a very small a value, so it's very concentrated. The corresponding wave form in the k space, when a is very small, would be very extended because the range goes like 1 over a. So it will look like this. Okay, so we have seen 4 examples, 2 extreme cases plus 2 intermediate cases. They all lead to the same conclusion, and that is you can use Fourier components or Fourier spectrum to construct simple harmonic waves in order to form the actual wave in k space, in real space or x space. But the more concentrated the wave is in x space, the more deconcentrated or delocalized the wave components are in x space, in k space, and vice versa. So here's our general conclusion. You look at a wave in x space, okay, psi x, and we plot it like this. So roughly speaking, the wave is concentrated within the range of delta x. We use the Fourier analysis to find the Fourier spectrum. So these are the simple harmonic components which will add up together to form this wave. And the simple harmonic components, the different k values, are roughly concentrated within this range. According to our examples, we found that there exists a relationship between delta x and delta k. They're sort of inversely proportional to each other, such that delta x times delta k, you multiply them together, one larger, one gets smaller, roughly of the order of magnitude 1. Okay, don't take that 1 too seriously, it's just the order of magnitude, not an actual number. This itself is well known in wave analysis, in Fourier analysis, and it is not an exclusive feature of modern physics. The difference here, the new thing here, is that this k is no longer just a wave vector. It has acquired a new meaning under the assumption, under the hypothesis of wave-particle duality. This k has acquired a new meaning because k is related to the momentum of the particle.